In this lecture, we are going to look at various different kind of operators, especially with a view of how they behave when you rotate your coordinate system. We have seen earlier that when we carry out a rotation Rn hat theta of coordinates, it acts on a quantum system via an operator Un hat theta. Of course, the form of that operator is specific to the particular system we are talking about. And notice that we are talking about passive rotations throughout, which means that it is not the system itself that is being transformed or rotated, it is the coordinates which are being rotated. Of course, that means that the numbers which we use to describe the state of a system must change along with, or may change along with the change of coordinates, and that change is described through this operator Un hat theta. As we have discussed before, this change could be described either by Un hat theta acting directly on the kets and changing them, leaving the operators intact, or we can also consider an approach in which the kets do not change, the operators are transformed according to Un hat theta inverse operator Un theta. You must realize that both of these approaches lead to exactly the same results as far as physically observable quantities are concerned. Now, in particular, a scalar operator is one which does not change under the rotation of coordinates. Strictly speaking, what we should say is a scalar operator is one for which the matrix elements for arbitrary states do not change under the rotation of coordinates. In particular, if we are using the approach that we will be using throughout, the one in which operators change, the operator for a scalar operator would have to undergo this transformation Un theta inverse S hat Un theta, but the result must be the same as the original operator S hat itself. So this is what a scalar operator is. Now, of course, if scalars are there, can vectors be far behind? So we have vector operators, which is not really one operator. A vector operator really is a set of three operators, which we call Vx, Vy, Vz, or V1, V2, V3, as is convenient for us, whichever is convenient. How do we characterize a vector operator or the set of three operators? We say that when we rotate our coordinates, the Vi change, of course, according to Vi become Vi prime, that is Un theta inverse Vi Un theta, which is the way all operators change. So the result must be this thing out here, a linear combination of the V's themselves, and not just any linear combination, exactly the same combination as happens to the coordinates. So basically, coordinates are the prototype. X hat, Y hat, Z hat are the prototypes of vector operators, and what we say is any set of three operators will be considered a vector operator if they transform under the rotation of coordinates in exactly the same way as the coordinate operators do, which is a an identical linear combination, of course, of the V components in this case. So this is really what a vector operator is. And since we are assuming in this picture that the kets don't change, the matrix elements of the expectation values of vector operator components transform exactly in the same way as the coordinates do. Now let us look at a specific example. If we rotate through an angle theta about the z-axis, we all know what would happen to coordinates, and what happens to vectors or vector operator components are exactly the same. So Vx becomes uz theta inverse Vx uz, which is the new Vx prime, and that's the same combination that we had for coordinates, Vx cosine theta plus Vy sine theta. A very similar thing happens for Vy prime, which is minus Vx sine theta plus Vy cos theta, and Vz prime, of course, stays unchanged because we're rotating, remember, about the x-axis. So Vz prime is the same as Vz. Now this happens for an arbitrary angle of rotation about the z-axis. What happens if I make theta infinitesimally small? We know that in that case, or for very small theta, Uz epsilon, so we are calling theta the small angle epsilon here. Uz epsilon is basically identity, which is what you would get for no rotation at all, plus a linear correction term which we have all seen before. It's I epsilon by h cross times j hat z, j hat z being the generator of rotations about the z-axis. Notice the plus sign here is because we are discussing passive rotations. Some books will have minus sign, that they will be discussing active rotations. Of course, all this is correct to order epsilon. There are order epsilon square corrections to this. Now if I take this version of Uz epsilon, plug it into the way in which the operator changes, of course the Uz theta epsilon inverse in front will become identity minus I epsilon by h cross jz plus higher order terms. Uz epsilon sitting here is of course just this, and if you calculate the thing through to order epsilon, it's pretty easy to see that what you will get is the transformation of a vector component Vi will be essentially Vi itself. That comes from the identity which is there in both Uz epsilon and Uz epsilon inverse, plus a first order correction term which happens to be minus I epsilon by h bar times the commutator of Jz with the vector component Vi. This again is something which you should be able to work out on your own, and in fact you have to work out on your own. Well, this is all correct up to order epsilon. There's an order epsilon square correction to this. But notice that when the angle theta is infinitesimal, cosine theta becomes cosine epsilon, which is 1 to order epsilon, the correction beyond that being order epsilon square, and sine theta simply becomes sine epsilon, which is epsilon to order epsilon. And if we use that, in particular Vx prime, which according to this formula is Vx minus the first order correction I epsilon by h bar, commutator of Jz with Vx, and this must be equal to what Vx becomes, that is Vx times 1 plus Vy times epsilon. And it's trivial to see that this can only be correct if you consider this term here to be exactly equal to Vy epsilon. And now cancelling out epsilon and moving things to the correct sides, we get the commutation relation between Jz and Vx becoming IH cross Vy, which, if you realize, is exactly the same commutation relation as we had between Jz and Jx. And that should not come as a surprise. After all, Jx, Jy, Jz are components of a vector operator on their own. So just like every vector operator, their commutation relation should be the same as here. We usually turn it on its head and we say vector operators behave this way simply because angular momentum components are vector operators, form a vector operator, and they have this commutation relation. Well, we don't stop here. This was only for Vx prime, that is the way Vx changes to Vx prime. If we look at the way Vy changes to Vy prime and Vz changes to Vz prime under the same rotation, we can easily figure out these two commutation relations. In fact, you should figure out these two commutation relations by explicitly working them out. So Jz Vy is minus IH cross Vx. Just remind you, Jz Jy commutator was minus IH cross Jx. And of course Jz commutator was 0, so is Jz Vz. This of course means simply that a z component of a vector does not change when you rotate through an angle, in fact any angle, not just an infinitesimal angle, about the z-axis. And all this together can be written down. Well, we worked this out only for Jz, but it should be easy enough for you to work it out for rotations about the x-axis and the y-axis, and check that in general, if you take the ith component of J and find a commutator of that with the jth component of V, the result is IH cross epsilon ijk Vk. Let me just remind you that that's exactly reminiscent of the angular momentum commutation relations in general, that happened to be Ji, Jj equals IH cross epsilon ijk Jk. By the way, some books take this to be the definition, these commutation relations to be the definition of the way vector of what vector operators are. It's a matter of taste whether you take the behavior under rotations to be the defining property for vector operators from which you derive the commutation relations, or these commutation relations as a defining property from which you actually can reconstruct via the Becker-Hausdorff lemma these rotation operators properties for finite angles. Whichever one you use, the other one can be derived from that. I personally find the rotation properties to be more geometric and meaningful, and so these I will tend to think of as defined results or derived results rather than definitions. But let me warn you, several books start with this as a definition. Now that we have the definition of vector operators, what examples do we have of them? Well, remember, as we said right now, any set of three components which behave like this, which have a commutator like this, or transform under rotations the way coordinates do, form a vector operator. And the most obvious example of this, of course, is nothing but the angular momentum operator itself. Well, most obvious if you take the commutation relation route, because here you can see that this obviously is one commutation relation which the angular momentum operators definitely satisfy. Well, another obvious set of three operators which form a vector operator, and this is obvious if you use the rotational properties definition. Remember, a vector operator is nothing but a set of three operators which transform like the coordinates. So the coordinate operators are obviously vector operators. Now that the components of the coordinate operator x hat, y hat, z hat obey this particular commutation relation, you can explicitly check. It's pretty easy to check this explicitly using standard rules like Li. There of course you will be using the orbital angular momentum operators L1, L2, L3, and using the fact that L1 is x2 p3 minus x3 p2 and the xp commutation relations, you can easily see that a commutation relation of this kind is satisfied by the position operator. But frankly, you didn't really have to check this. The position operators, after all, are the prototypes for vector operators, so it's obvious that they will have to obey this. Well, the other obvious candidate, and there are many more, but the other one which we will list here are the components of the momentum operator px, py, pz. Again, you can check that this commutation relation works just by explicitly calculating the commutator. But again, because px, py, pz are obviously components of a vector and they have to transform the way vectors do under rotations, the commutation relation itself should be sort of trivial.